Hey everybody. So we're going to try to do this lesson um, with a video. It's a little bit tricky because there's some stuff you need to see and it's a little bit confusing, but we will do our best with the resources we have available. So this is reflection. So we have to describe with numbers the phenomenon of reflection, describe simple optical systems consisting of both lenses and curved mirrors, and use ray diagrams to describe an image formed with curved mirrors. So reflection's really easy. We did this in Physics 20. Light as a particle or a wave will reflect according to the law of reflection, where your angle of incidence equals angle of reflection. So it's just saying that this angle and this angle are the same. Super easy. Okay. So because of the irregular nature of most surfaces, light reflecting off the surfaces does so in a random fashion and doesn't get a clear image. But if you have a mirror, it's smooth and it reflects it nice and perfectly, like a pond would do this too, right? It's nice and level, so you can get that light to reflect. So neither frequency or speed of the light is affected by reflection. So these are the examples that we did in Physics 20, where, okay, if this angle here is 28 degrees, then we know that this angle is 28 degrees. And all of these create a triangle, and triangles have to equal 180 degrees. So if we go 180 minus 28 minus 126, then we get this angle over here. So 180 minus 28 minus 126. And we get 26 degrees over here. And it's reflecting off of this surface, not circle. So if this is 26 degrees, then this is 26 degrees, right? So pretty easy. And we're not really going to do a lot of questions like that. Okay, so what we're going to focus on more is curved mirrors. So there's two types of curved mirrors. There's concave mirrors, which we call converging. And it's like a bowl, it's like a cave, right? Concave, it comes in, you can enter the cave. So satellite dish is an example of that. So what that allows light to do is light comes in or a signal comes in, it bounces off, and then it makes it reflect into this receiver here. So no matter what direction the light comes in as, it'll always go to that focal point there. Okay, the other types of mirrors are convex mirrors, where the surface of the mirror is curved outwards like a ball. So the mirrors, side mirrors, where it says objects in mirror may be closer than they appear, that allows you to see around corners a little bit better. So grocery stores sometimes have it in the corners where you can sort of see around the corners there. That's a convex mirror. So what we're going to learn to do is we're going to learn how to draw ray diagrams. And there's different parts of the ray diagram. So this here is called our principal axis, which is just that horizontal line. This is called our center of curvature, and this is our focal point, and this is our mirror. And then these lines on the mirror here represent the back of the mirror. So this is the shiny side, the front, and then this is side, the back. Okay, and then this point right here is called the vertex. So the reason that this is the center of curvature is a curved mirror is kind of like a bigger part of a circle. So it's kind of like this whole thing's a circle, and then the center is just the center of the circle, right? And then this focal point here is going to be half of the center, right? So what we know is 2f is equal to c. So this is f, this distance is f here, this distance is f here, and they're going to be the same. So we know that 2f is equal to c. And the focal point always appears at that halfway to the center point. So drawing ray diagrams. So to draw a ray diagram, objects are shown as arrows in front of the mirror sitting on the principal axis with the arrow tip representing the top of the object pointed up. Light rays can be drawn as straight lines leading from the top of the object towards the mirror in 3 possible directions. So these are our 3 rays that we draw on, and this won't make a lot of sense until we actually do a ray diagram. So the first one is parallel to the principal axis reflected through F, through the center C, reflected through C, and through the focus F, reflected parallel to the principal axis. Like I said, if that makes no sense, that's okay. You'll be like, oh, when we draw some actual ray diagrams. Okay, so when we draw ray diagrams, what they allow us to see is they allow us to see the characteristics of the object. So when you have an object in a curved mirror, it changes what the image looks like. So it's kind of like a funhouse mirror type of effect where you can be like shorter, taller, skinnier. So the terms that we use to describe the characteristics of our image are erect, I know, or inverted. So that's the term that they use. So we will be using erect. So an image sitting above the principal axis is erect and below the principal axis is inverted. The image can be larger or smaller, and then the object can be virtual or real. Okay, so larger and smaller makes sense. Virtual and real is a little bit confusing, so I will talk about virtual and real. Actually, before I do that, I'm just going to sort of show you this idea. So what I have here is I have a curved mirror, and then I just have a little frog that I can place in it like that. So I can show you a virtual or real image. So right here, you can see, it's hard to see in the camera, but inside there's the frog in there, but you see this image that's produced, and that's a hologram that we're producing. So that's our virtual image. Oh, I'm having trouble with the camera. There we go. So this is not the frog itself. The frog is inside here, but it creates this hologram sort of image that isn't really there. Okay, and all that we need to do that with is a curved mirror. So something else I could show you is the inverted or real. So here is my mirror, and what I can do is so you can see my hand. Actually, I'll put it down like that. And you can see that my image is inverted. My hand is going this way. We're not doing hand rules, don't worry. And then the image is upside down. But as I get closer and closer to it, what you'll see is now it's kind of out of focus and it's getting a lot bigger. And then as I continue to get closer, look, my fingers are in the same direction now, right? So it flipped around depending on where I was. So now I go backwards and you can see that it's flipped up. And as I move further away, my image gets smaller. So as I get closer, it gets bigger and bigger and bigger and bigger. And then we can't really see anything right here. And then, bam, it's right side up like that. So that's what we're going to talk about. Hopefully that helps. It's much better to see in person. You can see me. Oh, where am I? Hi. I don't know where I am. Hi. Hi. Okay. So concave mirrors are the principle behind projections and holograms. So if a screen is placed in a position where the image sits, it can lead to a focused image at that point. And we'll talk about what the screen is a little bit later. So think of it as a projector, like the projector in the classrooms. So if you place a screen somewhere, you can get an image on that screen and it can be focused. But if you get a virtual image, it sits on the opposite end of the mirror from the observer. So your bathroom mirror gives you a virtual image as you appear to be inside of the mirror, but you're not actually inside of the mirror. So that's a virtual image. So projectors get real images because that projection is outside of the mirror, and then inside of the mirror would be a virtual image. Okay, so what we're going to do is we're going to start by learning to draw ray diagrams, and ray diagrams help us predict the characteristics of the images. So there's 5 possible situations for concave mirrors. So all images produced in these situations will have the same characteristics. So sometimes you may need a line drawn behind the mirror, and these should be drawn as broken dashed lines. So the 5 cases are outside C, at C, between C and F, at F, and between F and the mirror. So we're going to draw ray diagrams for all these situations, and we're going to describe their characteristics. Okay, so This is what a ray diagram looks like. You have your C, you have your F, you have your mirror here, and then this is our object here. So that would be like my hand when I was showing you that. And what we want to see is what the image of the mirror, what the image is going to look like of my hand. So to figure out what that looks like, we're going to use a ruler, and we're going to draw a line parallel to the principal axis until it hits the mirror. I don't actually need the ruler, I'm just going to use a straight line, but you can use a ruler. And then what our line is going to do is it's going to reflect through the focal point like that. So that's the first line of our ray diagram. Okay. The second line of the ray diagram kind of does the same thing but opposite. So we're going to go through the focal point like this until we hit our mirror, and then we're going to go parallel to our principal axis, and this is our principal axis, so we do a parallel line. Okay, and then our last one, actually, well, I should say before we do our last one, you only need 2 of 3 lines to meet up. You only need 2 of these 3 lines to work. So we can already see where our image is produced. So our image is going to be produced right here where these lines match up, but we can just draw our third one. So our third one reflects through the center. We can extend our mirror a little bit there. So just pretend this mirror goes a little bit further. So it's going to hit our mirror, and then it's going to bounce back, and it's going to go this way. And you can see that all of our lines, switch to this, switch my color to red. You can see that all of our lines match up right here. So this is this red line that I drew on here. Get rid of this. Get out of here. Get out of here. Sorry. This one that I drew right here, that is what our image looks like. And our image, you can see, is upside down, so it's inverted. You can see that our object, which is over here, was 1 square big, and it's a little bit less than a square, so it's smaller, and it's real. So we know that it's real when it's on the same side of the mirror as the object. So it's a real image. So the characteristics are inverted, smaller, and real. Okay. So we'll do another one. We'll try another one. Okay. So this was when I was past C. Anytime I put an object past C, I'm always going to get an inverted, smaller, and real image. Okay. So we do the same thing here at C, where we go through parallel to our principal axis, and we reflect through our focal point. And then we go through our focal point, and we reflect off the mirror and go parallel to the principal axis. And our third line we can't really do because it's got to go through C and hit the mirror, but we can't really do that because I would just go straight down. So that's fine. We only need 2 of the 3 lines to hit, and we can see that, oops, this is where our image meets up, and you can see that our image is about 1 block big, so it looks like it's the same size. It's still upside down, so it's still inverted, and it's real because it's on the same side of the mirror as the object. So we produce an inverted, same size, real image. Okay. So this one here, we go parallel to the principal axis, reflect off the focal point, reflect through the focal point, reflect through the focal point, and go parallel to the principal axis. And for C, well, we can't really do that because that would bring us backwards. What we could do is we can reflect off of the mirror first, just extend that mirror, and then reflect back through C. It's hard to do to make it lined up. I didn't really line it up, but don't worry about that third line there. It's this what we want right here. So this is our image that we produce, and you can see it's inverted. You can see that it's real. It's on the same side as the mirror as the object, and it's bigger. It's more than 1 square big. Okay. So the only thing that changes so we started here outside C where it was smaller, and then at C it got same size, and then when we went between C and F it got bigger. And as we get closer and closer to that focal point, our image will get bigger and bigger and bigger, but it'll still stay inverted and it'll still say real. Okay. So if we draw one at F, so now our object is at F here. So we go parallel to the principal axis and then through the focal point. And we can't actually do the second line here because we can't go through the focal point and then reflect off the mirror. So what we have to do is we have to do our third line here. And to do that, I'm just going to use my ruler because we have to do it like this. So I'm going to line up my ruler just a little bit more like that. So you can see that my C and my arrow are in the mirror there, and I go bounce off my mirror like this, and then I bounce back this way and I go through C. Okay. And what you'll notice about these lines is these lines are parallel. So we're looking for an intersection between the lines, and if they're parallel, then they'll never meet up. So what this means is if we place our object at our focal point, we will never have an image. So there would be no image produced. And that's when I was showing my hand and it got a little blurry as I reached my focal point. Okay. And then the last case is between F and the mirror. So we'll start off with our first line. We'll go parallel to the principal axis, and then we will go through our focal point. Right? And again, we can't do our second line because we can't go through our focal point first and then hit our mirror. So we'll have to do the same thing that we did before. We take our ruler, line up C and F like that, and then we draw a line so it bounces off the mirror here and then goes back. So what we'll notice is that our lines, they're not parallel this time, but they're definitely not going to meet up over here. So where they will meet up is they're going to meet up on the other side of the mirror. We use a dotted line to show this. So if I want to, draw a dotted line, I think that went away. Yeah. So if I want to draw a dotted line, inside the mirror is a dotted line, and I just sort of keep that line going. And then I keep this line going inside of the mirror. So I just extend that line, and right here is where they meet up. So the image that I make is right here, like that. That's the image that I produce. So the characteristics of the image that we produce is it's definitely bigger, it's larger, okay? It's erect because it's above the principal axis, and it's virtual because now it's on the inside of the mirror there. So that's what our image looks like. Okay. So you need to know and memorize these characteristics. We'll do a summary chart at the end of the lesson to sort of sum all this up. And then, yeah. So the other type of mirror that we can have is a diverging mirror or a convex mirror. So when we draw our ray diagram for our convex mirror, we put our image over here because now we can see it bows out to us, and our focal point and our center are actually inside of the mirror. Okay, so this one's a little bit trickier, but what we do is we go parallel to the principal axis, and then we grab our ruler, and then that line, if that ray went inside of the mirror, it doesn't, it would go through the focal point there, but it's going to reflect off the mirror. So it's going to reflect like that. So that's going to be our first line that we draw on. But what I'm also going to do is I'm going to extend that line inside of the mirror here. So I'm just going to extend that line inside of the mirror. Oops, I wanted a dotted line. Like that. And you can see it go through that focal point there. Okay, so our second line is going to aim for that focal point to start. I guess we'll need our ruler again. So it's going to aim for that focal point to start. There it goes. Okay, so it's going to aim for that focal point, and then when it reflects off the mirror, it's going to go parallel to the principal axis like that. But what I'm going to do is I'm going to extend that line. Oops. Sorry, I want to extend the other line. I want to extend the reflected line right there. So I'm going to extend the line of the reflected ray like that, and that's good enough. So we call it a diverging mirror because we can see our two actual rays here diverge. They go away from each other. They're not going to meet up here. But what we do produce is we produce an image where those two lines meet up right here. So we produce an erect, smaller image, and because it's inside of the mirror, it's on the opposite side of our object, it's a virtual. So it's erect, smaller, and virtual. Okay? Yes, those are array diagrams. So there's practice in the homework for drawing those, and it lets us know our characteristics. Okay, so there is a formula that we can use as well. So when an object is placed between C and F, the image will be larger, and an object is placed outside C, the image will be smaller. So what that means is that there's magnification happening here. And in order to calculate how much larger or smaller, we can use this magnification formula. M equals high over ho equals negative di over do. So M refers to times magnification, 4 times, half times, 10 times magnification. High is the height of the image. Ho is the height of the object. Di is the distance from the mirror to the image. And do is the distance from the mirror to the object. Okay. So this formula can be found on your data booklet, and it can be found under waves. So here's the magnification equals high over ho, di over do. And this is the second one here is one we're also going to learn today. So the focal length can be used to help in calculations for the formula. So we also have this focal length formula as well, where 1 over f equals 1 over do plus 1 over di, where f is the focal length, di is the distance for the image, and do is the distance to the object. Okay, so when we're talking about object and image, what that means is, well, right, my hand is the object, and then the image is my hand inside of the mirror, right? We're talking about from the mirror to my hand and from the hand to my mirror like that, right? And you can see it flip. I'm at my focal point because we don't really get a nice image, and then it flips around like that, right? And I have a big hand there. Okay, so an important thing when doing these is your signs. So positives and negatives. Positives and negatives come into effect here. So our object, we always consider positive, okay? And because our focal length is on the same side as our object, we would also consider that positive here, right? Our distance is measured from our mirror, so this would be a positive distance. So our image is right here, that's our image. So it's still a positive in terms of distance, but since it's upside down, its height is negative, right? This would be a positive height, and this would be a negative height. So our height of our image, if it's inverted, would be negative, but everything else would be positive. Okay, so when we're inside of F, right, we got that image over here. So our object, we always consider positive, right? Our focal length is still on the same side of the mirror as our object, so that's still going to be positive. But since this is a positive distance, this must mean that it's a negative distance. So if it's virtual, its distance is going to be negative, right? And since it's erect, it's upright, same as our object, the height of our image is going to be positive. Okay, for a diverging mirror, our object is always positive, but now we see that our focal length is on the opposite side of the mirror. So this is important. This is key. This is what most people get wrong with diverging mirrors, is that your focal length needs to be negative, even if it doesn't tell you in the question, right? And since we produce an image over here, right, the distance to it is going to be negative, but since it's a rect, its height is positive. Okay, so these are really important, and you got to make sure you remember that this focal length is negative with diverging mirrors.
So this chart is something you should memorize and will help you on your test. So with a concave mirror, if we're outside of 2F, we are smaller. We are inverted, and we are real. If we're at 2F, we are same size, we are inverted, and we are real. And if we're between 2F and F, we are bigger, we are inverted, and we are real. Right, and you can see with all three of these, that they're all inverted and real. So we just get bigger as we get closer to that focal point. And then as we get to that focal point, we see that we get no image there. And then these last two are the only ones that are really different, right? Once we get inside of F, our size becomes larger. And then we become erect, and we become virtual, right? And then with a convex mirror, we are also erect and virtual, but this time we are always smaller. No matter where you put it, it's always smaller.
Okay, so let's do some calculations. The focal length of a converging mirror is 3 centimeters. A candle of 1 centimeter height is placed 3 centimeters past C from the mirror on the principal axis. So calculate the height of the image produced and list the properties of the image. So we can do this two ways. We can predict the characteristics by drawing a ray diagram. So let's do that first. So the focal length of a converging mirror 3. So each box must be 1 centimeter. So a 1 centimeter candle is placed 3 centimeters past C. So here's C, 1, 2, 3. So this is our candle here. So we just draw it as an arrow. I can't use a ruler on this, so I'll just freehand it the best I can. So my first line goes parallel to the principal axis and then through the focal point. Okay. My next line goes through the focal point and parallel to the principal axis. And you already see that your image produced is right here, but I can finish it off by making it go through C and then back through C like that, but we produce an image like that. And you can see that your image is smaller, it's inverted, and it's real. Okay. So that's one way. You can always use the ray diagram to figure out your characteristics, but we can also use the formula to calculate this. So let me just clear off that frog in that mirror. Okay. So we want to calculate the height of the image produced. So to do that, I always write out hi ho, di do, and you can sing your chant hi ho, di do, and your focal point as well. You need. Okay. So we know the height of the object. It said it's a 1 centimeter tall object, and we can leave everything in centimeters. Everything's going to be in centimeters. Okay, and then our focal length here is 3 centimeters. And we also know the distance of the object. So that distance of the object is from the mirror, right? So we placed it 3 centimeters past the center. So that means it was at 9 centimeters. Okay, and then we can use hi over ho equals negative di over do. And we can see if we have enough information. So we have do, and we have ho, and we want to find the height of the image, which we know is smaller. So we're trying to find this, but we don't have die, so it means we have to use our other formula first. So 1 over f equals 1 over die plus 1 over dou. Yeah. And we want to find die first. Okay, so to rearrange this, we subtract 1 over dou from both sides. So we have 1 over f minus 1 over dou is equal to 1 over die. Okay. And so to finish this off, what we have to do is if we go 1 over die, that equals die. So these cancel out and we just get die. But we'd have to do the same thing to the other side. So that's how we finish off this rearranging. We'd have to go like that. And these 1 overs don't cancel out because these two are added together. So we would go 1 over 3 centimeters minus 1 over 9 centimeters. And then we would 1 over that answer. Okay. So 3 minus 9, and then 1 over, and we get 4.5 centimeters as our answer. Okay, so now this is die, and we want to find high over here, so we can just move ho up top, and we're ready to solve using this equation. So negative die, which is 4.5 centimeters, and then ho is 1 centimeter, and dou is 9 centimeters. Okay. So 4.5, and we have to make that negative, divided by 9, and we get high of our image to be negative 0.5 centimeters. Right? And from our array diagram, we said it's smaller, which it is. We also said it's inverted. And that's what that negative represents. So that's good. We got that negative on there. And it's real. And that's the distance to our image is positive. So it's real. So we're good. So that's how you would do that question.
So a curved mirror produces a virtual image 2 times smaller than a 5 centimeter object. If the distance of the image is 3 centimeters, then what is the center of curvature? Okay. So we have high, ho, die, dou, focal length. And it's that focal length that we want to find. We just have to double it to find our C. So we have a curved mirror produces a virtual image. So virtual image means the distance to our image is going to be negative. We know that one's going to be negative. The distance to our object and the height of the object is always positive. And if we have a virtual image is always erect, so we know that's going to be positive there. Okay. So we have a 5 centimeter object, that's the height of our object, and it says magnification is 2 times smaller. So the height of our image is 2.5 centimeters. The distance to the image is 3 centimeters. We know that's virtual, that's negative, so we don't know these two. We have high over ho equals negative die over dou, and we also have 1 over f equals 1 over die plus 1 over dou. So we're going to use these guys. So because we don't know dou and we need it to find focal length, we'll have to use our first formula first. So high is 2.5 centimeters. Or I guess I should rearrange it first. Let me rearrange it first. Dou moves up top, ho moves up top, high moves down below. And then we can solve for dou, which will give us f, which will give us c. So negative 3 centimeters, because there's a negative there. Ho is positive 5 centimeters. And then our high is positive 2.5 centimeters. So if we plug that stuff into the calculator, so negative 3 times 5 will obviously give us positive 15. Oops, I put an extra bracket on there. Let's get rid of that extra bracket. Is 15. And then if we divide it by positive 2.5, we get our distance to our object, which is 6 centimeters. Okay, and now to finish it off, we get 1 over f equals 1 over dou plus 1 over die, and we 1 over it, and we can find f, so we're going to go 1 over 6 centimeters plus 1 over negative 3 centimeters, and you 1 over it, and you get your answer. So let's do that. You can see I switched dou and die, dou and die. It doesn't matter which one you make dou and which you make die because they're both added together. So just the negative has to be by the 3 and the positive by the 6. So if we go 1 over 6 plus 1 over negative 3, and then we 1 over our answer, and you end up getting that f equals negative 6 centimeters. So C is going to be 12 centimeters, right? And the negative tells us, oh, that's a diverging lens. Or mirror, sorry, not lens. That's a diverging mirror. That's 6 centimeters, which makes sense because dou was 6, the distance to our object, and then we find our focal length to be 6. Well, we're right at our focal point, but that doesn't matter for a diverging mirror. No matter where you put it with a diverging mirror, we're always going to be smaller and erect. So our next question is, a converging mirror has a center of curvature of 10 centimeters. Where should a 1 centimeter object be placed on the principal axis to achieve a virtual image of 10 times magnification? Okay, let's do this one here. So again, we have hi, ho, die, dou, and our focal length. So it says a converging mirror has a center of curvature of 10 centimeters. So my focal length is 5 centimeters. I don't know if it's, oh, it's converging, so that's positive. Where should I place a 1 centimeter object? So the height of my object is 1 centimeter. We don't know. Distance to the object, we don't know. That's what we're trying to find. And then we have a virtual image that's 10 times magnification. So that means that it's virtual, so this is going to be negative, but the height is erect if it's virtual. So this is positive 10 centimeters because it's 10 times the magnification. Okay, so again, we'll go hi over ho equals negative die over dou. And then we have 1 over f equals 1 over die plus 1 over dou. Okay, and we don't know these two, right? Which makes it hard to do this question, and it also makes it hard to do this question. So this is a tricky question. This is a special type of question. So what we have to do in this question is, I'm going to move up there. We're going to combine these two formulas. We're going to combine these together, right? So if I move that dou up there, we know that dou, hi, is 10 centimeters. Ho is 1 centimeter. And that equals negative die, right? I'm just going to move the negative over here. So what this tells us is, if I just answer for this, negative 10 dou is equal to die. So we can use this now, and we can insert that into this equation. So 1 over f is equal, oh, and we know what f is, right? So 1 over 5, I'm not going to put any units in, is equal to 1 over negative 10 dou, right? Because die is equal to negative 10 dou plus 1 over dou. And now we only have one thing that we're solving for. So this is a little bit tricky, but what we have to do is we have to multiply by a common denominator. So if we do that, I think if we just multiply everything by negative 10 dou, or even just 10 dou. Let's just make this negative because that's the same thing. So we'll multiply everything by 10 dou. 10 dou. So we'll multiply everything by 10 dou, that common denominator. So this is going to be 2 dou, because 10 over 5 is 2. And then we have dou. And then we have negative 10 dou over 10 dou is 1. And then the dou's will cancel out 10 over 1. So we have that. And then we get 2 dou is equal to 9. So I move the 2 down there, and dou is equal to positive 4.5 centimeters. Right. And that makes sense because we have a converging mirror. We're inside of F. That's all good. And that's what we're trying to find. Where should a 10 centimeter or 1 centimeter object be placed? To get 10 times magnification, it would want to be placed at 4.5 centimeters. That is our answer.
Okay, so this is your homework. Give that a go. Let me know if you have any problems, and